Hello viewers, welcome to today's lecture on packet switching. In the last lecture, I have introduced to you the switched communication network, and in switched communication network different types of switchings are done, and one of them is circuit switching. In the last lecture, I have discussed in detail the circuit switching technique and how circuit switching is done, its advantages and limitations we have discussed in detail. Now, in this lecture, I shall first identify the limitations of circuit switching technique, which will give you the background for packet switching. However, before I discuss packet switching, there is another technique which is known as message switching, which essentially can be considered as the first step for packet switching. So, in this lecture we shall discuss about packet switching, and here is the outline of the lecture. As I mentioned, first I shall discuss the limitations of circuit switching, which I have discussed in the last lecture. Then I shall introduce to you the message switching concepts and explain to you how it overcomes some of the limitations of circuit switching technique. And then there are some disadvantages of message switching technique which can be overcome by using packet switching. So, I shall introduce to you the packet switching concepts, and as we shall see, there are two different techniques used in packet switching. One is known as virtual circuit packet switching, another is known as datagram packet switching. So, I shall discuss both of them in details and then compare the datagram versus virtual circuit packet switching techniques, compare their relative advantages and disadvantages, and then we shall see there is a possibility of combining datagram and virtual circuit. For example, it can be internal datagram, external virtual circuit, like that, having 4 combinations. I shall discuss about them in details, and finally I shall conclude my lecture with discussion on circuit switching versus packet switching. On completion of this lecture, the students will be able to understand the need for packet switching. They will be able to understand how packet switching take place. They will be able to understand how different types of packet switching techniques that is used, namely datagram and virtual circuit. Then they will be able to distinguish between virtual circuit and datagram type packet switching, and finally they will be able to compare circuit switching with packet switching. So, let me first start with the problems that is present in circuit switching. As you have seen in the last lecture, the network resources are dedicated to a particular connection in circuit switching. As we know, before any data transfer can be done, a path has to be established, and that path remains active until it is terminated, whether data is sent or not. So, and it is fully dedicated for that particular session. And there are two important shortcomings, particularly when you use data communication. For example, in a typical user host data connection, the utilization is very low. As you have seen, even for voice, the utilization is not very high, particularly when the traffic is bursty, as it happens in user host data connection, then the utilization will be very, very low. And also it provides facility for data transmission at a constant rate. That means it does not allow variable data rate. As you have seen, the links between the nodes have much higher data rate capability. This is by using TDM and FDM techniques. And moreover, they use those better, the transmission media of higher bandwidth, such as optical fiber, coaxial cable, and for them it is possible to transfer at a higher rate at intermediate points, but that cannot be done in circuit switching. Obviously, data transmission pattern, which is burst in nature, may not ensure this constant rate of flow, and ultimately it limits the utility of this circuit switching technique. And these limitations can be overcome by using message switching. The basic idea of message switching is each network node receives and stores the packet, stores the message essentially, determines the next leg of route and queues the message to go out of that link. That means here what is being done, it is essentially a store and forward approach. Message is stored, that means nodes are provided with some buffer, and they are stored until a link is available or a path is available in the direction of the destination. So the queues of message go out on that link. So obviously it has to do routing, and then on that route the message can be sent in the form of queues. Here the advantage is line efficiency is greater. Line efficiency is greater because it is being shared. Here, as I have mentioned, it is essentially a store and forward approach. So a particular link at any point of time can be shared by a number of source destination pairs. That means a message is sent, the next moment another message is sent, so a queue is formed, and from that queue the messages are sent. So as a consequence the link is shared, and data rate conversion is possible. For example, from one node, let me have a look at the diagram that will make it clear. Here for example, this is the station A which is sending data to station D. So this is the source, this is the destination. Now as you can see, each node is provided with a storage. This is shown by this symbol. So that means there is a storage capability at each node. So this storage is able to store the messages. So A will store the message in node 1, then from node 1, if the destination is D, it can go via this route from 1 to 2. That means when the path is available, it is free, that message can be sent to 2, then from again it will be stored here and until this path link is available again. That means in both these places the messages are stored and queued and then to the destination node where the station is connected, and then it comes to 6, and from where it will go to the destination station D. So this is how it takes place. And as a consequence, as you can see, data rate conversion is possible. That means here for example, this may be a slow link A to this particular node 1. So here data transfer rate can be small. On the other hand, whenever it is sent from node 1 to node 2, data can go at a much higher rate. Not only it can go at a much higher rate, one can use different encoding technique. For example, depending on whether it is a analog line or a digital line, one can do encoding or modulation depending on how it is done. So data rate conversion is possible and encoding can also be done. So even under heavy traffic, packets are accepted possibly with a greater delivery delay. That means in this particular case, in case of circuit switching, in case of heavy load, a path may not be available, it may be blocked. But in case of message switching, if there is heavy load, then still this node will keep on accepting messages. However, the delivery will be delayed, and delay will take place in the delivery, but the packets will be accepted, and the outcome is the delay, nothing more than that. And another important characteristic is that whenever the messages are queued and stored in the storage, it is possible to assign some priority to them. That means the high priority traffic, real time traffic, can be given higher priorities and they can be sent fast before simple data traffics can be sent. So these are the advantages of these message switching technique. And obviously, let us see how exactly it occurs. So here for example, from A to C it is going. So first it will go from node A to node 1 to node 2, the entire message is sent, then it is stored there for brief duration, and there may be some delay. As you can see, there is some delay in this direction. You have got the time, and so here you have got the time in this direction. So again it is stored here for some duration, then again from node 4 it goes to node 5 where this destination station is attached. So this is how message goes from a node to another node, and each place it is stored and there is some delay, and then the entire message is sent. This thickness or the width of this line essentially is showing the volume of the message, the size of the message. The bigger is the message, wider will be this particular line. So this is how the message communication take place. Now what is the disadvantage of this? Obviously message switching overcomes some of the limitations of circuit switching. Is there any disadvantage of this? Disadvantage is that whenever the message is large, obviously there is no restriction on the limit of the message. It can be very, very large. In such a case, what will happen? It will monopolize the link and the storage. That means whenever a message is stored here, it will occupy a large storage area. That means other messages which is coming from other directions cannot be stored here. It will monopolize. Similarly, whenever transfer is taking place, it may take very long time monopolizing the link. And so if very large messages are sent, it will not only lead to long delay, but it may monopolize the link and storage. So these are the disadvantages of message switching. That's why this message switching concept has been extended to another technique known as packet switching. So this new form of architecture for long distance communication, it is being used since 1970. It was first used in ARPANET, as we shall see later. ARPANET used packet switching technique to overcome the limitations of circuit switching. However, the packet switching technology has evolved over time. Although it was in use in 70s, over the years the technology has improved, it has evolved. However, the basic technology has not changed. The basic concepts, the basic technology has remained the same. And packet switching remains one of the few effective technologies for long distance data communication. So nowadays, particularly for wide area network, this packet switching is the technique used in the internet. Let us see how it is being done. First of all, data transmitted in short packets, few kilobytes, not very big, so that it can overcome the limitation of message switching. So a longer message is broken up into series of packets. So if you have got a long message, as it is shown here, it is broken down into several packets, packet 1 to packet n. Every packet contains some control information in its header required for routing and other purposes. The header will contain some information like source address, destination address, then the sequence number. So this information is necessary for control. So each such packet is provided with this information: source address, destination address, and sequence number. Not only this, if it is necessary to perform, say, error detection and error control, then the packet must be provided with a trailer, and trailer usually is provided with that CRC. So that means a packet may have a header, then you have got the packet, that means your data, and it will have a trailer. So this is the formation of a frame of a packet, and this is how a message is broken down into a number of packets. Here only header is shown, however trailer may also be present. So as mentioned earlier, a packet switching network breaks up a message into packets. And as I mentioned, there are two approaches commonly used for handling these packets. One is known as virtual circuit, another is known as datagram. First we shall consider the virtual circuit approach. In virtual circuit approach, a pre-planned route is established before any packets are sent. So, it is somewhat similar to circuit switching, that is why it is called virtual circuit approach. So, essentially it is packet switching. Again here the store and forward approach is used. However, just like circuit switching, some route is established, there is a pre-planned route, that is why it is called virtual circuits, although effectively it is store and forward approach used in packet switching. So, call request and call accept packets are used to establish the connection. Then the route is fixed for the duration of the logical connection like circuit switching. Here there is no dedicated path, only the route is fixed. That does not mean it is not shared. So, it is being shared by other source destination pairs, only thing is it follows the same route, and each packet contains a virtual circuit identifier as well as data. That means along with the data some virtual circuit identifier is provided. That virtual circuit identifier is used to route the packet through the packet switch network, and each node on the route knows where to forward the packets. That means the node need not really do the routing, only thing after receiving that virtual circuit identifier, it finds out where to forward, in which direction to forward. Finally, a clear request packet issued by one of the two stations terminates the connection. So, just like circuit switching, it is also having some kind of three distinct phases. First of all, a route is established, then the packet transfer takes place, then with the help of a clear request the route is terminated. Here let us see how it really works. So, from A it has to go to C through nodes 1, 2, 4 and 5. So, through the circuit switch network, as you can see, call request packets are sent, and since it is a packet, this call request packet is also stored and forwarded here. So, there will be some delay, as you can see there is some delay before call request packet is sent to the next node. Then again another call request packet goes to the next node, and ultimately the other side will send call accept packet, and call accept packets are also stored and forwarded just like any other packet. It goes in the reverse direction, and when it reaches the source node where the packets are originating, the packets may be sent one after the other. As you can see, now the thickness is smaller than the message. So, this is essentially tells you the size of the packet. So, one packet is sent from one node to 2, then the same packet, you see here 2 packets are going from 1 to 2 and 2 to 4. So, some kind of parallelism is being performed, and again now you can see 3 packets are going, 3 packets of the same message, and finally in this way the packets will reach the destination. So, a single message has been divided into 3 packets, and all the 3 packets are going in this manner, and because parallelism is possible, it takes much shorter time. And finally, acknowledgement packet comes and the link is terminated. So, in this way the acknowledgement packet will come from in the reverse direction, and as it reaches the source node, it can be terminated. So, this is how the virtual circuit packet switching works. So, we have seen that the virtual circuit packet switching, one main advantage is that the same message, different packets of the same message can go parallelly, just like it is somewhat similar to pipelining that is used in processors. So, these are the main characteristics of circuit switching, virtual circuit packet switching. Routes between stations is set up prior to data transfer, as I have already shown. So, a packet is buffered at each node and queued for output over a line. That means here, just like message switching, here also the packets are buffered, but since the packets are of smaller size, it does not monopolize the buffer. It does not occupy larger storage, and also it does not take long transmission time. As a consequence, the link is also not monopolized. So a data packet needs to carry only the virtual circuit identifier for effective routing decisions. As I mentioned, the virtual circuit identifier is used for the purpose of routing. The nodes does not perform any routing operation, except it uses the virtual circuit identifier for forwarding the packets. So as I mentioned, intermediate nodes take no routing decisions, often provide sequencing and error control. As I said, some kind of sequencing and error control may be provided. In that case, CRC is provided and suitable ARQ technique can be used, as we have discussed earlier. Now coming to the datagram approach, it is different from the virtual circuit. Here each packet is treated independently with no reference to packets that have gone before. In the previous case, we have seen all the packets of the same message goes through the same route, but here it is not so. Each packet is treated independently as a separate entity, just like what we do in postal system. Suppose say 5 volumes of a book, if you send through post office, there is a possibility that if you send say volume 1 today, volume 2 after 2 days, volume 3 after 3 days, volume 4 after 4 days, volume 5 after 5 days, but at the destination there is a possibility that volume 3 will reach before earlier than the volume 1, or volume 4 will reach before volume 5. So similarly, in datagram approach, this situation can happen just like postal system. And here every intermediate node has to take routing decision, because each packet is treated independently and there is no predetermined route. As a consequence, each node has to take routing decision. So it keeps there is an overhead on the node to perform routing decision. However, this routing decision can be taken care of with the help of the source and destination addresses provided as part of the packet. So packet should contain the information about the source address and destination address, and based on that this routing decision is performed by the intermediate nodes. Usually intermediate nodes maintain routing tables. However, there are various routing algorithms, routing techniques. We shall discuss about them in the next lecture. Let us see how the datagram packet switching works. So here we see a packet is going from 1 to 2, then another packet is going from two packets are going 1 to 2, and another packet, the previous packet is going from 2 to 4, and 3 packets are going 1 to 2, 2 to 4, and 4 to 5. So packets of the same messages are going, and as we see there is no call request or call forwarding delay. So each of these packets can go independently. What is the advantage? Advantage of this datagram approach is that call setup phase is avoided, fully avoided. There is no call setup time required like that circuit switching or virtual circuit switching. So for transmission of packets, datagram will be faster. That means here it will take shorter time, because it is more primitive and it is more flexible. So it is quite flexible, because whenever there is some congestion or failed link can be avoided. So it is more reliable. So here the advantage is, in virtual circuit, as we have seen, each and every packet of the same message has to go through the same route. But suppose a link fails in between. In such a case, the subsequent packets cannot be delivered, cannot go to the destination, or if there is some congestion on one part of that node, in such a case that packet delivery will take very long time. This can be avoided in datagram approach, because it is more flexible. Each node can take the routing decision, So, if there is any failed link, if there is any congestion in the path of the packet, then what it will do, it will simply send the packet through some other route. So, it is not necessary that the packet 1 of a message will go through a particular route and packet 2 has to follow the same route. It can go through a different route, and as a result the different packets can reach out of order. So, as I mentioned, packets may be delivered out of order. So, this is a disadvantage. That means, since the packets are delivered out of order, the receiver must store all the packets, then they have to order them to form the message. So, message has to be formed by combining the packets before it can be forwarded to the upper layer of the software. So, the destination node will require much processing power and storage space, so that all the received packets can be stored and then they can be combined to form a message and then can be forwarded to the upper layers. And as a consequence, if a node crashes momentarily, that suppose some packets are coming and it crashes momentarily, that may lead to problem. All of the queued packets are lost. In such a case, all the queued packets will be lost. So, these are the two problems or disadvantages of datagram approach. So, let us now compare between the datagram packet switching with virtual circuit packet switching. So, in virtual circuit, node need not decide route. That virtual circuit identifier that is for identifier that is being generated while performing the routing, that call request using the call request and call acknowledgement signals, that identifier is used to perform the route. So, the nodes can be very simple in this case, and it is more difficult to adapt to congestion. As I have said, if there is any congestion in the network, it cannot really take care of. So, it cannot adapt to the congestion, because all the packets has to go to the same route whether there is congestion or not, and it maintains the sequence order. So, as I mentioned, all the packets are going to the same route. So, all the packets are delivered in order. So, the messages, the packets need not be reordered in the destination node, destination station. As a result, it is advantageous. Each packet can be forwarded to the upper layer without forming the complete message. And as I mentioned, all packets are sent through the same pre-planned route, that is the typical characteristic of virtual circuit. On the other hand, in datagram service, each packet is treated independently. We have seen that although they belong to the same message, but each of them is considered as a separate entity, and as a consequence, when for the purpose of routing, each of the packets can be sent independently through different routes, depending on the availability of path, depending on congestion, depending on failure of links. And call setup phase is avoided. So, this because of this, there will be lesser delay. So, delay will be less because of this call setup phase is not required, and inherently more flexible and reliable, as I have already mentioned, because it can adapt to congestion, it can adapt to failure, and it can deliver the packet more reliably compared to virtual circuit. Now, there is a question about the packet size. We have seen that a message is broken down into smaller size packets. Question is, how small? Should it be very small? Obviously, as we shall see, that cannot be done. As packet size is decreased, the transmission time reduces until it is comparable to the size of the control information. So, there is a close relationship between packet size and the transmission time. So, as you have seen, if the size of the packet is large, transmission time will be longer. If the size of the packet is small, transmission time is smaller. On the other hand, there is another important parameter. As I said, a packet will have header and trailer, and header and trailer bytes will be the overhead. So, if the size is very small, then the overhead will be much higher, although transmission time will be shorter. Let us take up an example to illustrate the situation. Here it is assumed, let us assume that there is a virtual circuit from station A through nodes 1, 2 and 4 and 5, same example, to station C. So, message size is 32 bytes, packet header is 4 bytes. So, here whenever the number of packet is 1, that means essentially it is message switching. The total number of bytes is that is being sent is 108. So, it is shown in this diagram. For example, this is the header 4 bytes, and here is the data 32. That means 4 plus 32, that means 36, and then it will require 3 hops. So, 36 into 3, that means so many bytes are to be transmitted, that means 108. That is what I have shown, 108. That will be the transmission time, the total transmission time. We are assuming here that there is no time needed for storage and there is no other processing time. Propagation time is very, very small. So, assuming that propagation time is small, transmission time will be the time required to send 108 bytes. So, depending on the data rate, this time will be different. Now, let us consider whenever it is each message is divided into 2 packets, as it is shown in this diagram. So, here we see each message is divided into 2 packets. So, this is message 1, this is message 2, this is message 3 of message 1 data 1 data 2, message 2 data 1 data 2, message 3 data 1 data 2. So, here as we see, the transmission total number of bytes to be transmitted is 120. However, because of parallelism, you can see here this packet and this packet is being sent simultaneously. This packet and this packet is being sent simultaneously. As a consequence, the total transmission time will be shorter. So, here we find the transmission time has decreased. Although more number of bytes are transmitted through the network, the overall transmission time, source to destination transmission time, has reduced from 108 to 80. That is a normalized value, you can say. Now, as you increase it further, that means if you divide into 4 packets, it can be explained in the same manner. If we do it in the same manner, then you will find that the transmission time that will be required will be 72. And again, and however, if we increase the packet size further, say divide the message into 8 packets, we find that the total number of bytes become 192. However, the transmission time is now increased to 80, because the overhead is essentially the benefit of parallelism is compensated, or because of this higher number of bytes is essentially is responsible for this higher overhead, is responsible for this longer transmission time. And if it is divided into 16 packets, total number of bytes to be transmitted is 288 and the transmission time is 120. So, what does it indicate? It indicates that if you plot a curve, say on this, if it is packet size, and here is the transmission time, as the packet size is increased, number of packet by packet size as it is increased, as you can see here, for smaller packets it takes longer time, for longer packets it takes also longer time. So, there is a optimum packet size. So, when the transmission time will be smaller, this is the transmission time. So, transmission time is small for some intermediate value, some value in between maximum and minimum. So, we find that in this example, in the previous example, whenever the message is divided into 4 packets, each of 8 bytes, then it gives you the minimum transmission time. So, this clearly shows that packets should not be too large. That is why we have come from message switching to packet switching. The packets should not be too small, then also the transmission time will be longer. Now, as I mentioned, that there is a possibility of external and internal operation. That means whether we are using virtual circuit or datagram. We have seen that in the network we have got stations connected to nodes, and nodes are also communicating. So, when the station is connecting to the node, that is external to the switched communication network. On the other hand, node to node communication is essentially part of the switched communication network. So, that is why that external means from station to node, internal means from node to node. So, there in both the cases it can be virtual circuit or datagram. So, there are 2 dimensions of the problem. At the interface between a station and a network node, we may have connection oriented or connectionless service. Internally, the network may use virtual circuits or datagrams. This will lead to 4 different scenarios. Let us explain each of them one after the other. First one is the external VC and internal VC. So, in both the cases it is virtual circuit. So, whenever it is external VC and internal VC, as you can see, virtual line is created, virtual path is created. For example, we are sending from 1 to D and 1 to C. So, virtual circuit is A to 1 to 2 to 6 to D. On the other hand, another virtual circuit is A to 1 to 3 to 5 to C. So, these are the 2 virtual circuits. It can be in the other way also, say 1 to 2 to 6 to 5 to C, that is also possible. So, there can be overlapping, but here incidentally these are not overlapped. So, we find this virtual circuit is created from end to end, source to and station to station. So, in such a case, all the packets originating from A for C and D, obviously they will be having some sequence number, we will follow this route. The packets with the destination D will go from A to 1 to 2 to 6 to D. On the other hand, all the packets with destination address C will go from A to 1 to 3 to 5 to C. Follow the same route depending on the destination. So, this is your external VC and internal VC. Then comes the second scenario. In this, the network handles each packet independently. That means external virtual circuit, internal datagram. So, the network handles each packet separately. That means, since the internal is datagram, you see here the external is virtual circuit. So, since it is virtual circuits, it will be given in this order. However, since it is internally it is virtual circuit, here 1.1 this packet can go in this route, the other packet can go in this other route, the third packet can go in the different route. Similarly, this 2.1, 2.2, 2.2, as it enters the network, switch communication network, then it may follow different routes. However, the network buffers packets if necessary, so that they are delivered to the destination in the proper order. That means, in this node these packets are buffered, although within the network it comes in different sequence, then they are delivered in order. As you can see, in the same order it has what was sent from A has reached destination D 1.1, 1.2 and 1.3, because it was stored in this node 6 and it was buffered here, and then they have been ordered in the proper sequence. Similarly, the packets with the destination address C has been stored in packet in node 5, then they have been ordered properly with the number 2.1, 2.2, 2.3, although it may come from different routes. So, this is your external VC and internal datagram. Coming to scenario 3, where it is external DG and internal DG. Here, as you can see, a packet, here the packets can be delivered out of order, and once it enters the network, inside the network also it may go through different routes. Since it is external datagram, the nodes do not buffer the packets or arrange the packets in proper order. The way it is received here is sent to the destination, because it is external datagram, and as a consequence you find that the packets have reached the destination out of order. Although 1.3 was sent at the end, it has reached the destination earlier than 1.21 and 1.2. Similarly, 2.2 here has reached earlier than 2.1, although it was given to the node 1 earlier than 2.2. So, you see here in both the cases the packets have reached out of order, which is possible in case of external datagram and internal datagram. In both the cases we are using the datagram, and so each packet is treated independently both from user's end as well as from network's viewpoint. That is why the packets are reaching out of order from the at the destination. Now, let us come to scenario 4. Here it is external datagram and internal virtual circuit. So, here we find external datagram means here it can be given in any order. However, as it is given in a particular order inside the network, switched communication network, there is a virtual circuit. So, the packet, since it has been given in this order D.1, D.2 and D.3, as you can see, they are going through the network in the same path and following the same sequence through the same virtual circuit. So, here also the order in which the packets are provided to the node, in the same order it goes, because inside it is virtual circuit. Similarly, from A to C also we find that the C1, C2 and C3, they have been presented in the same order to node A, and you can see here that C1 has reached earlier than C2 than C3. So, this is the route that is being followed by the through the virtual circuit that is being created between node 1 and node 5. However, externally it is datagram. So, you see the 4 situations, the external datagram and internal datagram, where how and here we have seen how internal paths are created and the packets are delivered at the destination using external datagram. Now, we have come to the conclusion part of the lecture, where we are comparing the 3 techniques: circuit switching, datagram packet switching and virtual circuit packet switching, because these 3 techniques have emerged as the key techniques used in switched communication network. So, in circuit switching we have seen that a dedicated path is created from source to destination, and that path remains valid, and that path is used for sending the message. And in case of datagram packet switching, no dedicated path is created. As you have seen, each packet is treated independently. And in virtual circuit packet switching also no dedicated path is created, because in both these cases the paths can be shared by other packets of other source destination pairs. And in circuit switching, as you have seen, path established for entire conversation. As I mentioned, whenever in case of circuit switching, just like your telephone network, whenever we dial and after we get the destination receiver successfully, then the link is established, and for the entire conversation the link remains established whether somebody talks or not. On the other hand, in datagram packet switching, routes established for each packet. That means for each packet, we have seen that each packet is treated independently in case of datagram packet switching. As a result, route established for each packet separately, and in case of virtual circuit, route established for entire conversation, that means for all the packets of the same message. So, these are the differences between these three. Now, let us come to the call setup delay. We have seen that the circuit switching has call setup delay. Call setup delay is necessary for establishing the path before any data transfer. In datagram packet switching, there is packet transmission delay. There is no call setup delay. In datagram packet switching, we have seen that the packets are stored and then forwarded. There may be delay if there is a big queue, there may be delay in transmission. So, packet transmission delay is there. In virtual circuit packet switching also there is call setup delay and packet transmission delay. Then coming to the fourth point, overload. See, in case of circuit switching, overload may block call setup. That means, if the circuit switched network is blocking type, if there is heavy traffic, for example, whenever it is implemented with the help of multi-stage cross-bus switches, in this case it can be of blocking type. In such a case, when there is heavy load, there is a possibility that it is not possible to set up the link. So, here even the link path cannot be set up, so data transfer is not possible. But in datagram packet switching, as we have seen, even when there is overload, only the delay will increase, but packets will be accepted by the network nodes and they will be stored and queued. However, when in case of overload, there may be long delay. In case of virtual circuit packet switching, overload may block call setup. Just like circuit switching, there may be blocking in call setup. If path is not available, then call setup cannot be done, and also it increases the packet delay. So, you can see here in the context of overload, the virtual circuit packet switching is not really very good, because it may lead to blocking of call setup and also delay is there. Then, as I mentioned, in circuit switching there is no speed or code conversion. Since all the data has to go through the same path, so it is the guaranteed bandwidth is provided, big or small, and there is no conversion in between, not possible. So, if the sender is sending at the rate of 64 kilobits per second through the entire path, the data will go at the rate of 64 kilobits per second. On the other hand, in case of datagram packet switching, speed or code conversion is possible. As I mentioned, from the station to the node, it may be, say, if it is a analog line using modem, we can use suitable modulation technique. On the other hand, from one node to another node, it can be time division multiplexing, and data transfer can take place at a much higher rate, and code conversion is possible. So, various encoding techniques and different speeds are possible in intermediate nodes. That is true not only for datagram packet switching, it is also true for virtual packet switching. Then the circuit switching techniques gives you fixed bandwidth. Fixed bandwidth means once the network is set up, it gives you the fixed bandwidth in circuit switching. On the other hand, in virtual circuit packet switching or datagram packet switching, in both cases the bandwidth can be dynamic, because in different paths you can have different speed and conversion times. So, it is possible to have dynamic bandwidth in datagram and virtual circuit packet switching. Only thing possible is, since it is being shared, that bandwidth will be dependent on the load. Then in case of circuit switching, we have seen there is no overhead bits after call setup. After the call setup is done, there is no overhead bits. After the path is set up, for example, in case of telephone connection, once the connection is established, you can simply talk or sing whatever you want, and there is no extra overhead. On the other hand, whenever in datagram packet switching or virtual circuit packet switching, overhead bits is in each packet. As you have seen, in datagram packet switching, you have to do the routing. So, you have to provide the source address, destination address, sequence number for control purposes, and if you are using error detection and control, you have to use CRC. Similarly, that is true in case of virtual circuit packet switching. In both the cases, overhead bits are present in each packet, not only in the call setup delay, but subsequently. So, this gives you the comparison of the three switching techniques that we have discussed in this. We have discussed one circuit switching we have discussed in the last lecture, and in this lecture we have discussed the datagram packet switching and virtual circuit packet switching. So, now it is time to give you the review questions. Question number 1 is how the drawback of circuit switching is overcome in message switching. Second question is what is the drawback of message switching, how is it overcome in packet switching. Third question is what are the key differences between datagram and virtual circuit packet switching. Fourth question is distinguish between circuit switching and virtual circuit packet switching. Fifth question is how packet size affects the transmission time in a packet switching network. So, these are the 5 questions which will be answered in the next lecture. Coming to the answer to the questions of lecture 18, first question was what are the 3 steps involved in data communication through circuit switching. As we have seen, there are 3 basic steps. First step is circuit establishment, that means call request with the help of that call request and call acknowledgement. So, with the help of call request and call acknowledgement, circuit establishment is performed. Then the circuit maintenance during the data transfer, when the data transfer is going on, that circuit has to be maintained. So, since the circuit has to be maintained for the entire duration, the circuit maintenance operation has to be performed by using suitable signals. Then comes the third step, that is circuit disconnect. When the data transfer is over, that circuit has to be disconnected. So, these are the 3 steps in circuit switching as we have discussed in details. Then the second question was mention the key advantages and disadvantages of circuit switching technique. The advantages of circuit switching techniques I have emphasized many times. The advantages are after path is established, data communication takes place without delay. Only delay involved is the propagation delay, propagation time. And data without delay, very suitable for continuous traffic. Obviously, the circuit switching is very suitable when there is a stream traffic, continuous traffic is being sent from the source to destination. Then it establishes the dedicated path we have seen, and there is no overhead after call setup, and it is transparent, and data transfer is transfer in order. As I mentioned, whenever a circuit switch network is established, then whatever is sent in the same order, it reaches the destination. So, if you send data or packets will reach in order, and this is the advantage of the circuit switching technique. The disadvantages are it provides initial delay for setting up the call, and as I mentioned, it is inefficient for bursty traffic. Third question was, disadvantage is data rates should be same because of fixed bandwidth. Fifth disadvantage is when load increases, some calls may be blocked. That means it may not be possible to set up the link. Then the third question was, why data communication through circuit switching is not efficient? Answer is, in data communication, traffic between terminal and server are not continuous. Sometimes more data may come and sometimes there is no data at all. Circuit switching is not efficient because of fixed bandwidth, because circuit switching provides you fixed bandwidth, but in data communication, because of the bursty nature of traffic, this fixed bandwidth is not suitable, rather dynamic bandwidth is suitable, which cannot be provided by circuit switching. That is why it is not efficient. Fourth question was, compare the performance of space division single stage switch with multi-stage switch. Answer is, space division single stage switch requires more number of cross points, as you have seen. It is non-blocking in nature, but provides no redundant path. On the other hand, multi-stage switches require lesser number of cross points, blocking in nature, it is blocking. The multi-stage switches can be blocking in nature, but provides redundant paths. So you see, there are advantages and disadvantages. Here you have got more cross point, here the number of cross point is less, here it is non-blocking, here it is blocking, here there is redundant path, here there is no redundant path. So you see, there are advantages and disadvantages in both the cases. Fifth question was, distinguish between in-channel and common channel signaling techniques used in circuit switch network. Answer is, in-channel signaling technique uses the same band of frequencies used by voice signals to transmit control signals. So same, that means the signals can reach wherever the voice can reach. On the other hand, common channel signaling uses dedicated channels to transmit control signals, and this dedicated channel is common to a number of voice channels. So with this we come to the end of today's lecture. In the next lecture we shall discuss about the routing in packet switch network. Thank you.